All right, welcome back, welcome back. Today we're going to talk about ionic compounds and how they dissociate in water. First of all, let's go ahead and look at an ionic compound. Here we have normal sodium chloride, otherwise known as table salt. And remember that ionic compounds are actually salts. I know when we think salt, we always think of table salt, but there are actually different kinds of salt. So, we know that table salt is composed of positive sodium cations and negative chloride anions, and they are bonded together with an electrostatic charge. Basically, the negative and the positive bond together. That's review. So, when I take this solid, remember this is a crystalline lattice, this is a solid at room temperature. If I take this and put it in a beaker full of water, what will happen to it? Well, as it turns out, the water molecules which are in this beaker, all of this is composed of water molecules, will make this ionic solid dissociate. These chloride anions and sodium cations will basically break apart and float around in the water. And this also becomes an electrolyte. So why does that happen? Well, we haven't gone over covalent bonding, but this is a water molecule. This is a molecular compound. It has two hydrogens and one oxygen, and it is bonded covalently. Don't worry about that right now. All you need to know is that when it does bond, the hydrogens tend to be slightly more negative than this part of the molecule, which has oxygen. And this is slightly more negative. There's a term for this. It's called polar, because these are two poles. They're different, positive and negative. Polar covalent. So, it is a polar covalent compound. Now, when I put this solid in here, these crystals in here, the hydrogen parts down here, which are a little bit more positive, will start to attract the chloride negative anion. And the sodium, which is a little bit more positive, will be attracted to the oxygen, which is a little bit more negative. So all of this, when it goes into water, is just broken up into little bitty cations and anions floating around in this liquid. And there's a term for that. It's called aqueous. Aqueous means it is more or less in this solvent. The solvent is the water. It's just floating around in there. And these are positive and they are negative. And that is also why this will conduct electricity when you put a charge in here, because electrons will be transferred. But let's talk about how we actually write this out. That's what you need to know for the test. How do I write this out? Let's go down here and look at this. Here we have sodium chloride. First of all, let's look at these little things here. This is S. What does that S stand for? This means solid. This AQ means aqueous, which means these ions are floating in water. Now you're probably thinking, why don't I put H2O over here? Because this is in H2O, it's in water. Well, that's because this aqueous basically tells us it's already in water. So we don't need the H2O. All we need to write is the ionic compound on the left-hand side of the equation and the cations and anions on the right-hand side. Now the equation is separated by this little arrow. This little arrow just tells us that this side of the equation has the reactants, which is sodium chloride or whatever we put on this side, and this side we have the products. Think of it as an equal sign. Now later this gets a little bit more complicated because sometimes they have arrows that point back, and that's all about equilibrium, but do not worry about that for right now. So now this is going to break apart and float around. When I break these back apart, remember this is electrically neutral. This ionic compound has no charge. But when it breaks back into its ions, I have to put the charge back on the cation and the anion. So that seems very simple. I just break it apart and put the charges back on. Now, the one thing that's hard about this I've noticed is that students have a hard time figuring out the charges on these. They don't know what the charges are. Remember, that all goes back to the periodic table. Cl, chlorine, chloride. If I go to the halogens, group 17, these tend to gain 1 electron. Everything in here is going to be a -1 charge. Remember when we practiced this. So that's going to be a -1 charge. I just put a minus. Sodium is in group 1. Everything over here is a +1 charge. Everything here is a +2. Now these transition metals and these metals here and stuff here sometimes vary. Aluminum's are always going to be a +3. Zinc's a +2. Silver's a +1, which we've gone over. So silver +1, zinc +2, aluminum +3. We do not need Roman numerals for those. Remember that. And everything in here, these transition metals can vary. Now this group 13 or 3, a lot of times these are +3 charge, but the problem is some of these, like gallium, can have different oxidation states. So it's really a good idea to get into the habit of putting Roman numerals for this stuff. So I have to go back to my periodic table to understand the charges and then write them out. That seems basic. Let's go down to something a little bit harder here. Another example. Well, now I have a polyatomic ion. I have to memorize these. This is sulfate. Sulfate, if I memorized it properly, has a 2- charge. Of course, that makes sense because both of these have a +1 charge. Now, let's think about this for a brief second. What is this 2 really telling us right here? This 2 is telling us there is a sodium cation that has a +1 charge, and there's another sodium cation with a +1 charge. What is this 4 telling me here? This 4 is telling me there are 4 oxygens bonded with that sulfur. But this is all together. This is a polyatomic anion, so there's really only one SO4. This is floating around together in the water. This is going to be one thing floating around together, and these will be floating around. So when I write this out, notice how that 2, I put it in front of the sodium cation, and I still have to put the charge on because there's 2 of them. There's 1, there's 2. So that little subscript is now in the front, telling me I have 2 sodium cations in my water, plus I have 1 sulfate anion with a 2- charge floating around. So really I have double the amount. When this dissociates, I have 2 times the number of sodium cations than sulfate anions. Okay, well, let's go down here and see what else we got. Well, our old friend NH4, which is ammonium. The ammonium cation. Sorry, it's easy to get ammonia and ammonium confused. The ammonium cation NH4. Remember, the 4 is inside the parentheses. That we can't change that. That just tells us this is NH4. It has a +1 charge. But there's 3 of them. So I have NH4 and I have an NH4. Like I say, when in doubt, write it out. If I see a 3, if you're confused, write out the 3. I have 3 of them. Over here I have PO4. PO4. But there's no parentheses. There's no number outside of them. This is a polyatomic anion. There's a name for this. It's called phosphate. It's a 3- charge, or -3. And that makes sense. I have 3 of these. I have +1, +2, +3. And that cancels out this -3. Now, how do I write that out? That 3 goes in front of the NH4. I have 3 of them. 1, 2, 3. 3 NH4 cations with a +1 charge in water. Plus I have 1 phosphate polyatomic anion with a 3- charge. Going on down. Well, we have sodium again. That's always going to be +1. That makes sense. And these are easier. Notice how these are just, there's no subscripts down here. I have one sodium cation. I have one hydroxide anion. I already know sodium's +1. I know hydroxide's -1. On a test, that's easy. So I'm going to put in. Now, you're probably thinking, why do I need this plus here? Why do I need this minus? Because if I put Na, that is actually sodium. That is not sodium, a sodium cation. It's a different thing. This is sodium. This is sodium when it has one less electron. That's why I have to make sure the charge is over here so people know that. Otherwise, I'm basically telling them something else. This is a language. And in my language, I got to make sure people know what I'm talking about. Well, we have potassium. Yet again, this is easy. I have one. I have a potassium and I have a hydroxide. So -1. So hydroxide's -1. Potassium is +1. Okay, now we got down here. And a little bit harder. I have one right here. One magnesium. So I just got to put the charge. And that's in group 2 of the periodic table. That's how I know it's a +2 or 2+. And right here, that 2 outside of the parentheses tells me there are 2 hydroxides. Okay, well, that was a little bit of practice. Let's go and look at this worksheet that's actually in the packet, because chemistry teachers love worksheets. Okay, well, I have an oxygen here. You're probably thinking, how in the heck do I know that oxygen has a -2 charge? And that's not just oxygen, that's oxide. That's called an oxide anion. Yet again, everything here is -1. Everything here is -2. And this is -3. I just go find it. Here's oxygen. It's got to be a -2. So I have oxygen, -2. And that tells me something. That tells me that that iron, which is a transition metal, right here, that iron must be a +2. And I always tell people, figure out the anion first. Figure out the anion and the charge, and then go and figure this out, because sometimes these are transition metals. I have to know the anion to figure out the state, the oxidation state of the transition metal. Sulfur. Yet again, sulfur is in the same group as oxygen. It's -2. Now, yet again, this confuses people. If I see a little subscript there and it's not part of a polyatomic anion or polyatomic cation, see, that's part of sulfite. I just put 2. Na. Sodium is in group 1. Sodium has to have a +1 charge. Now, theoretically, I would put aqueous down here. Aqueous. I'm not going to put aqueous on all of these. There's not a lot of room. Okay, we have chlorine, chloride, anions. There's 2 of them. See how that 2 went right there? Theoretically, there's a 1 down here. So that 1, I don't have to put a 1 though. That 1 would go right here. Now I put calcium. Not a lot of room in here. Okay, what's the charge on this calcium? These chlorides both have a -1, so that's basically a -1 plus a -1. That's -2. So that calcium has to be +2. Which makes sense because guess what? It's in group 2, which is always +2, and these are always +1. Wow, look at this jumbled mess. Okay, first of all, remember, always figure out if you're looking at a polyatomic anion. And that's what I'm looking at. This is sulfite. Sulfite has, and there's 3 of them. There's a sulfite, there's a sulfite, there's a sulfite. Every one of these has a 2- charge. So that 3 is right here. 3. 1, 2, 3. And here's the sulfites, and they have a -2 or 2- charge. That tells me something right there. Aluminum. There's 2 of them. See that little subscript 2? Just put your 2. AO. Now, what's the charge on this? Well, this side's going to be -6 total. I got 2 plus 2 plus 2. That's -6. So I have 2 of these. Each one of those has to be plus 3. See how that works out? Plus 3 plus 3. This positive 6 cancels out that minus 6. Plus, you know what? I hate to keep bringing up the periodic table. It's getting awkward for me. But if I look at the periodic table, guess what? Aluminum is in group 3 or 13, which tells us it's probably a plus 3 charge. And I already told you, memorize aluminum. It's always a plus 3 charge. Zinc's plus 2, silver's plus 1. So you should already know that. Going on down. Remember, you should have aqueous here. What the heck is that? That's actually nitrate. 1 minus charge. And here we have our good friend ammonium again. Ammonium. Plus 1. It's one of those few plus positive cations. It's plus 1 minus 1. Here's the danger here. A bunch of people would say, oh, 4. They're going to put this 4 over here. Or they're going to put a 3 over here. Remember, you gotta look at this. Divide this up. Say, okay, what is this? Oh, this is a polyatomic anion. This is a polyatomic cation. Okay. Oxygens. Yet again, periodic table is your friend. Minus 2. Minus 2. But guess what? How many of them do I have? Take that 3. Just put it there. O. 2 minus. What is this telling me? I have iron, but I have 2 of them, right? So they have to be plus 3. Makes sense. This side's a little bit easier because now I'm doing the anions. It's easier to do the anions than the cations, especially when they are already giving me the charges of the cations. All right, so what do we got here? This is potassium hydroxide. That one's confusing because OH is hydroxide, but you need to memorize, and it's a minus charge. Okay. Okay now. All right, what do we got? NO3. Okay, what did we say NO3 was? NO3 is nitrate. But how many of them do I have? I have NO3. When in doubt, write it out. Then I have another NO3. I already know it's a minus charge. This is a minus charge, minus 1. So I have to put 2 NO3 minus. People might also get this wrong. They might start combining these charges. Oh, this is minus 2. There's 2 of them. You don't need to do that. This is telling me I have 2. NO3s are both a minus 1 charge. All right. Almost there. Remember, you got to put aqueous there. We have aluminum chloride. Well, we already know aluminum is plus 3. We went over that earlier. And we already know chloride is minus 1 because it is a halogen. How many of them do I have? 3. 3. Chloride anions. Aqueous. Okay, here we have copper sulfate. And that sulfate is going to be a 2 minus charge, minus 2. I just got to remember that. Memorize your list. Okay, well, here's the danger. Some kid is going to do it. I know they're going to do it. They're going to put a 4. Oh, it's 4. SO. That would be wrong. The polyatomic ion never dissociates. So I'm going to put SO 4 2 minus. And that's basically how you write dissociation equations when you are given the ionic compound. Now, since we're running out of time, I'll probably make one more video where I do this worksheet. On this one, notice how you have to do the whole thing by yourself. So this is something you definitely want to know for a test. So I'll make another little short video on that. But I hope that helped you.